Hello and welcome. In this video, we'll be diving deep into matrix operations using Python. We'll explore how to perform key mathematical tasks like matrix addition, subtraction, multiplication, finding the transpose, cofactor, and even calculating the inverse of a matrix. I'll walk you through the code step by step so that by the end of this video, you'll have a clear understanding of how to implement these operations in Python. Let's get started. We are importing the numpy library here, which is essential for mathematical operations involving arrays and matrices. In this code, this library is specifically used to calculate the determinant of matrices. This line defines a lambda function called list2d, which generates a 2D list matrix filled with zeros. The function takes two arguments, r number of rows and c number of columns. It uses a list comprehension to create rows and fill each element with 0. This is used to initialize empty matrices when needed. Now matrix display function. This function, mdisp, is used to display a matrix M in a visually neat format. It first prints a separator line using print. Then, it prints the name of the matrix and a message, if any, like matrix A added successfully. For each row in the matrix M, it prints each element with proper spacing, ensuring they are aligned for easy readability. Another separator line is printed to close the output. This function is called throughout the program to display matrices in a user-friendly manner. Now, a check for square matrix. This function checks if a given matrix M is square. A matrix is square if the number of rows is equal to the number of columns. If it is square, the function returns true. Otherwise, it returns false. Many matrix operations, like finding the trace, determinant, or inverse, can only be performed on square matrices. So this function is used to verify whether the input matrix qualifies. Now for matrix addition, subtraction, and multiplication. This function adds two matrices, A and B. First, it retrieves the number of rows R and columns C of the matrix. It initializes an empty matrix RES using list2d, R, C. The function then loops through each row I and column J of the matrices, adding corresponding elements of A and B and storing the result. Finally, it calls mdisp, RES, to display the resulting matrix. For subtraction subfunction, the structure of the subfunction is similar to the add function, except it subtracts the elements of matrix B from A. For multiplication mul function, and matrix multiplication is more complex. It first checks the dimensions, R1, C1 for matrix A, and R2, C2 for matrix B. The matrix RES has dimensions R1 by C2, because the result of multiplying two matrices has the number of rows of the first matrix and the number of columns of the second. Then it performs the multiplication using 3 nested loops. For each element, it sums the product of corresponding elements from A's row and B's column. Finally, it displays the result using mdisp function. Now, for matrix trace. This function calculates the trace of a square matrix A. The trace is the sum of the diagonal elements from the top left to bottom right. A loop runs through the matrix, adding the elements where the row and column indices are the same. Now, for matrix determinant. This function calculates the determinant of matrix A. Instead of manually coding it, we use numpy's built-in det function, which is highly optimized for such calculations. Now, for minor calculation. First, create a 2D result matrix, set row and column offset to 0. Iterate over the matrix if the value matches with a given position. Decrease the offset by 1. Now assign the values from input matrix to result matrix as per the positions shown and return the matrix. The cofactor of a matrix is a signed minor of the matrix elements. The cofactor matrix is a matrix where each element is replaced by its corresponding cofactor. This cofactor function will be further used for calculating adjoint and inverse of a matrix. This function only works when the matrix is a square matrix, as determinant calculation is only possible in a square matrix. The function takes a matrix A. It calculates the number of rows, R, and columns, C, and then initializes the result matrix. RES is initialized with the same dimensions as a using list 2D, R, C. Now iterate through the input matrix. Now calculate the sign factor P based on the current row and column indices. Calculate the determinant of the minor matrix using the det function and round it 2 decimal places. Assign the calculated cofactor value to the corresponding position in RES. Return the calculated cofactor matrix RES. Now for a transpose of a matrix. The transpose of a matrix is a new matrix where the rows become columns and the columns become rows. In simpler terms, it flips the matrix over its diagonal. The function takes a matrix A as input. Then for determining rows and columns, it first calculates the number of rows, R, and columns, C, of matrix and initialize result matrix. The result matrix RES is initialized with dimension C cross R. Note that the rows and columns are swapped. We use the list2D function to create this matrix of zeros with swapped dimensions C, R. Transpose operation. The next part is the double for loop, outer loop, for each I, which corresponds to columns of the original matrix A. Inner loop, for each j, which corresponds to rows of A. It assigns the element at position of A to position of RES with swapped dimensions. This effectively swaps rows and columns. The function returns the transposed matrix RES. Now for adjoint of a matrix. The adjoint of a matrix is the transpose of its cofactor matrix. Input. The function takes a matrix A, cofactor matrix. It first calls cofac A to compute the cofactor matrix of A. Transpose. The result from the cofac function is then passed to the transpose function to obtain the adjoint matrix, which is the transpose of the cofactor matrix. Return result. The adjoint matrix is returned. Now for inverse of a matrix. Input. The function takes a matrix A, adjoint matrix. It first calculates the adjoint of the matrix A using adjoint A and stores the result in M. Determinant. It calculates the determinant of matrix A using the det A function. If the determinant is 0, the inverse cannot be computed, but this calculation is done in the menu function. Inverse calculation. It initializes a result matrix RES with the same dimensions as A. Then, using nested loops, it divides each element of the adjoint matrix at the position by the determinant of A and rounds the result to 2 decimal places. This is stored in RES. The function returns the inverse matrix RES. Now for matrix input and data storage. This block allows the user to input matrices and stores them for further operations. Matrix name. The user is prompted to input a name for the matrix stored in NM. Row and column input. The number of rows, R, and columns, C, are taken as input from the user. Matrix initialization. A new matrix mat is created using list2D, RC, which initializes it with zeros. User input for elements. Using nested for loops, the program takes input for each element of the matrix by prompting the user with a position like enter 1, 1, first row, first column. The user-provided values are stored in mat I1, J1. Store in mat_data. Once all elements are entered, the matrix is stored in the mat_data dictionary with its name as the key. Display matrix. Finally, the matrix is displayed using disp with a success message. Now for menu for matrix operations. This function displays the main menu for matrix operations and prompts the user to choose a task. The menu function first prints a neatly formatted menu with options for various matrix operations. AM. Add new matrix. D. Display all matrices. TR. Trace of a matrix. DT. Determinant of a matrix. A. Add matrices. SB. Subtract matrices. M. Multiply matrices. T. Transpose of a matrix. C. Cofactor matrix. AD. Adjoint of a matrix. I. Inverse of a matrix. User input. The user is prompted to enter a task inp. This input will dictate which operation to perform next, and based on the input, the program will call the corresponding function. And here goes the output for each matrix operation. That's it. We've now gone through matrix operations in Python, from basic tasks like addition and subtraction to more advanced ones like finding the cofactor, adjoint, and inverse. I hope this video helped you understand the code and the logic behind it. If you found this tutorial helpful, don't forget to like and follow for more coding tutorials. Feel free to drop any questions in the comments below. Thanks for watching and happy coding.